maybe not yet. Just check.
It started recording.
Okay, all right.
I will share my screen.
Thanks everyone for joining today's HEP-TN Seminar. It's a great pleasure to have Luca Tagliacozzo, who's also a friend from long back, to give today's seminar. And today, Luca will tell us about universal features of out-of-equilibrium systems. So thanks, Luca, for agreeing to give the seminar, and please go ahead.
You're welcome. So first of all, I want to start with also thanking you for being interested in the things that I'm currently doing. And this work has been developed together with Eric Toni that you see here on the left, smiling. And this is Jacopo, that is my student that is currently finishing his PhD. He is not as smiling as Eric, but hopefully he will survive. You can find everything in this preprint. That is, that has been accepted finally in PRB, rapid communication. So it should be out in an updated version soon. And the subject I will talk about is universality out of equilibrium, and I will first try to motivate why I'm interested in such a thing like universality out of equilibrium. So this is a bit the outline. I will go very fast onto the background because I think that here more or less anyone knows the background. And then I will maybe spend a few more minutes on talking about quenches, because I think at least most of us are a bit more used to working at equilibrium. And I will then describe what we observe in specific quenches. And so the spoiler of the results is just this one. So I will define everything carefully. But the main thing is that here we have time on the x-axis, and we have the entanglement spectrum. And I will discuss in detail what it means. And what we see is that looking in the right variables, despite that there is a strong out of equilibrium evolution going on, nothing seems to happen at the level of the entanglement spectrum, right? In this middle box here, everything is flat. And so that's something we want to understand better, why that's happening. Okay, so this is the results. So we will give some partial explanation to what we observe in this kind of plots. But let me first start with some background and motivation. Please, at any time, feel free to interrupt me. I will pause at the end of any section to ask for a question explicitly, but don't hesitate in interrupting me, okay? So obviously, the context is that of quantum many-body systems in which, as we know, even if we have finite local Hilbert space, as soon as we take several constituents, the state of the system is described by a huge tensor. This is CI1 to IN, that is a tensor with n indices, and this contains exponentially many numbers, okay? And that's a typical exponential growth we're used to. So beyond order 40 to 50 constituent or spin 1/2, let's say, if we only are considering a local Hilbert space of dimension 2, we can hardly simulate things on a classical computer. Okay, so how do we deal with that? Well, actually, we can try to approximate the state of our system by a specific class of state. And in particular, one can easily understand that if instead of writing generic states, one write product states, so states in which every constituent is independent, you only need to specify n numbers, n vectors. So if we are in a two-dimensional Hilbert space, we have to specify two complex number per vector times n, and this obviously is not exponentially large, so we can describe these states. But product states are typical of systems that do not interact, or in certain bases do not interact, and so we would like to be able to go beyond that. And tensor network and matrix control state in particular are extension to these states, to a situation in which now the state is not a product anymore, but mathematically still a product of rather than vectors. So let's say the elements of my tensor the numbers inside my tensor are obtained by taking traces of products of a set of matrices. Okay, and so these again tell us that the number of variational parameter only scale linearly with the size of the systems once these matrices have fixed dimension. And one can easily convince himself that one of the property of these states is that if we consider a region made by consecutive spins or constituent, then the entanglement of that region is upper bounded by the logarithm of this size of the matrix square. Okay, so what these states are states that are able to describe systems that have a certain amount of entanglement, but not an arbitrary one if we keep the dimension of the matrix fixed. So I've been talking of entanglement. About entanglement, let me just define it for pure state. So given a pure state in a tensor product Hilbert space, we can divide it in two parts. For example, here I have a state made of a line of constituent, a spin chain, and then I define as A the region in which this square region here, I hope you can see it, and B the exterior of that. And then a state is entangled if it's not a product of the state of A and B, meaning that what happens in B is not independent on what happens in A. Okay, and then in order to understand what's going on in A, if I'm only interested in observing things inside A, I need to trace over the degrees of freedom in B, and I'm typically left with a mixed state if the state is entangled. That is called the reduced density matrix of A, and a possible measure of entanglement, for example, is the von Neumann entropy of that mixed state. Okay, that's the entanglement entropy. Another interesting object that I will discuss about today is the spectrum of that mixed state. So I take that mixed state is positive definite, so I can express it as the exponential of a certain matrix that in field theory is called the modular Hamiltonian. And then the spectrum of this guy here, this HA, is called entanglement spectrum. And typically I will order the eigenvalues from the smallest to the largest. These eigenvalues in general can be ordered. The spectrum can be continuous, discrete, but in my case, since I'm on a lattice, it will always be discrete. And I will be interested in understanding what happened to these entanglement Hamiltonian. Okay, and so a way to understand what happens, since in general Hamiltonians can be shifted and rescaled pretty arbitrarily, then
sorry, Luca, I think
yes.
that there was a question in the chat window.
Yes, please.
I can maybe yeah, so I can just read it out. So is there any reason to believe why states might naturally evolve towards or concentrate on matrix product states?
No, I don't think there is any reason to believe that. I mean, we know that ground state of local Hamiltonian have a gap in one dimension are well described by matrix product state. But I don't think that there is any reason to believe that when you evolve something, so I'm thinking of an auto-equilibrium evolution, the states evolve towards matrix product state. So for the moment, I'm thinking of this class of states as an approximate class of state that I can use to make better prediction than if I use product state. But we will have to discuss about it, and I will do it in following. I don't know if I answered the question. Should I continue?
Yes, I don't see any further questions. Yeah.
Okay. So I was saying that I'm interested in general in understanding what this HA is for specific cases, and I will talk about it. But since HA can be shifted and rescaled, then in order to get rid of the shift, I consider its gap, so the difference between the eigenvalue R and the first one. And then in order to get rid of rescaling, I consider the ratio of the gaps. Okay. Yes?
Why can H be shifted and rescaled?
So typically in so for example, if rho A is normalized, and so we know that the trace of rho A must be equal to 1. And so this is a constraint, right? So, and typically, if you're interested in comparing this Hamiltonian with certain Hamiltonian of field theories, in that Hamiltonian, there is not such a constraint. So we have to allow for this kind of shifting and rescaling if we want to compare it with some known theory, let's say.
I see. So if after I normalize the density matrix, then there's no freedom to shift and scale.
Once I normalize the density matrix, there is no freedom to shift and rescale, indeed. But that density matrix could have come from something that if you unshift things looks different. Okay, so that's the idea.
Let me just make sure. So if I start from an unnormalized density matrix and then normalize it, so now I have two different HAs. Do you mean this GR over G1 is the same for the two different HAs?
Yes, exactly. So this would be exactly. So that's exactly the point. So you get rid of all these kind of ambiguities.
Thanks.
Okay. Okay. So now I wanted to discuss. So I've been talking about entanglement and matrix closed state, and the connection between the two. We said that matrix closed state are good just to describe states that have a finite amount of entanglement in a region of consecutive spin. I didn't prove that, but you have to believe me. And then one question is, what are the states relevant for? And here there is a plot from a paper by Latorre, Rico, and Vidal in 2004, in which they actually show that numerically, and then there have been proofs and things that for gapped system, you see this is the entanglement as a function of the partition size in an infinitely large system. You see that if the system is gapped, the entanglement tend to saturate to a finite value, and then we expect that these states can be simulated properly with matrix closed state. If the state is critical, then the entanglement grows logarithmically with the size of the partition. And then in principle, these states are problematic for matrix closed state with fixed bond dimension, okay? And so somehow these states are not naturally described by matrix closed state. So we already have one example, just to answer the question in the chat, we already have one example. So ground state of critical systems are not correctly described by matrix closed state with fixed bond dimension. Okay, so but nevertheless, now I'm trying to justify why I'm interested in universal things. So nevertheless, the idea is that if we are able to minimize the energy of, let's say, a state described by matrix closed state with fixed bond dimension, and here I put the example of a 1D Hamiltonian that for h equal to 1 we know is critical. So these are the plot of the entropy of the ground state of this Hamiltonian, and this blue line is exactly at h equal to 1. I can still try to see what happens if I approximate my state with this matrix closed state, even if I know that the answer won't be the correct answer. Okay, and the idea, yes.
So the gap states, you should understand those as below the critical point. So those are
yes, h different from 1, let's say.
So h below 1,
or even above 1 for a matter of interest. So it's just h equal 1 that is critical.
Yeah, I guess I was trying to understand which. Should I interpret h less than 1 as a phase transition?
No, sorry. H different from 1 is gapped. And then h exactly equal to 1, that's the phase transition. Okay, so it's a critical.
What I meant was a second. So the h equals 1 is the critical point, second order phase transition, yeah?
Yes.
H less than 1 would be a first order phase transition, or h greater than 1 would be a first order phase transition.
No, it would be actually a gapped phase, so there would be no transition. So, so this model has Pauli X and Pauli Z operator. So for h equals 0, so or less than 1, let's say, everything is aligned. So the ground state would be just a product of more or less a product of plus state where the plus is the eigenstate of sigma x. For h larger than 1, the ground state will just be a product of let's say, down spins, where down is the eigenvector of sigma z with eigenvalue -1. So basically, these are two product states. So they are gapped. The ground state of gapped Hamiltonian, they will be a bit modified, not exactly this, unless h is infinite or 0. But let's say all points around those things can be described by mathematical product state with finite bond dimension. And the problem is at h = 1, where there is this critical point.
Yeah, so I guess my question would be, if you took it in a critical state and then you quench the system and you look at the evolution, is this the direction of travel that your talk is going in?
Yes.
Good, thank you.
Okay.
I have another question.
Yes.
So this blue plot, this is still a gap approximation of your gapless Hamiltonian, right?
So in this case, so the simulation here is done with free fermions, so there are no MPS. Okay. So here is just a plot that shows what happens to the entanglement entropy.
I see. Yeah.
Okay.
Thanks.
So now I'm getting to what I think you're thinking about.
Okay.
On the next slide. Okay. So that's a bit what has been said. So now if we try to encode this critical state with MPS with finite bond dimension, what we observe that actually, if here there is a critical point that is h = 1, what happens is that we open a gap in our system, and the larger the bond dimension, the smaller the gap is. So we get closer and closer to the critical point, and by minimizing the energy, we really kind of get the short distance physics correct, but our state will always be gapped. So the correlation will always decay exponentially at large distances. Okay, but nevertheless, since there is the phenomenon of universality close to second order phase transition, we still are able to extract some useful information from this approximate simulation. That's a bit the main idea here. So that, for example, if we are interested in, so at this critical point, we have what is called the spectrum of critical exponents. So all correlation length decay algebraically with some exponent that I call it delta, depending on the operators. And so from analyzing correctly our results at finite bond dimension with MPS, we're able to actually extract these critical exponents. Okay, and for example, I have here, so I show here how you would do that, and basically, or I show you here what is going on. So basically, you can take this Ising model that we used before. You see here I put h = 1 exactly, and now I studied it on a finite chain with periodic boundary condition and minimize the energy of my answer by keeping the bond dimension fixed. And let's observe what happens. So here I have the results of the numerical simulation that were published in this paper here with Bogdan Pirvu, Frank Berstreit, and Guy Vidal. So here you see you have the size of the system in a logarithmic scale. So the size increases in this direction. And here we have the error in the energy, again in a logarithmic scale. And we know that the exact solution, so if we were able to reproduce exactly the physics, we know from CFT that the energy of a chain of length L minus the energy of a chain that is infinitely would go with something like 1/n squared. And that's proportional to 1/n squared with the central charge times some number as a proportionality factor. And this is this black line here. And so now different color represents results for different MPS simulation with different bond dimension. And you immediately see that for some time, for a small enough system, the MPS capture the physics pretty well. But then it deviates and saturate. The energy becomes only dependent on the bond dimension and not on the size of the system anymore. You see, it becomes flat. And so obviously we are very far from the correct results. But nevertheless, if we plot the last points of this series here as a function of the bond dimension in this inset here, you see some scaling. There is again a log-log power law going on. And so we see that actually we can interpret these results as if at the given bond dimension we have a certain finite size that more or less is the one in which we completely transition from these two regimes. So we can associate a scale or a correlation length to the system that has a given bond dimension. And actually, if you now take it seriously and do a scaling plot, so scale things in terms of this correlation length that is induced by the finite bond dimension, all the data that I showed previously collapse on a single curve. Okay, and so we see that even though the entanglement scaling is wrong of our answer, we can still use our answers as an approximation, and due to the onset of universality, we will be able to extract the information we are interested in. In this case, for example, the critical exponents. So before taking question, I want to mention that these the same thing has been observed with Philippe in 2 dimensions. So now here the system is a 2-dimensional system of fermions hopping with nearest neighbors, first neighbors repulsion, and actually it's on the honeycomb lattice, and we are at half filling, and so basically, as if we ramp up the repulsion, we expect that the fermions will occupy 1 every second site. But then as the repulsion goes down, these kinetic terms kind of dominates and the fermions delocalize. And so we go from a charge density wave to a semi-metal through a second order phase transition here that was first characterized with quantum Monte Carlo in this paper in 2004. And then a natural order parameter is the difference between the fermions on site A and B of the lattice. And so if we study the system with HEP-TN, and all the simulations have been done by Philippe in his group, so we see a very similar effect where for any finite bond dimension of the PEPs now, so the PEPs is now a tensor network that is now 2-dimensional and has bond dimension D here on this auxiliary leg, we see a very similar effect that can be retraced to the appearance of a finite correlation length here that goes to 0 as D goes to infinity and allows to extract all critical exponents. Okay, so what I'm discussing is not specific to 1D, but is really general, and it's due to the fact that we are not able to really exactly encode the ground state of a critical system on this tensor network, but we can only approximate it. And here you see it's very different, the role that entanglement plays, because in 1D you could have said that the entanglement was wrong in the ansatz. Here in 2D, you can't say that because at this specific critical point, the state is still an area law state. The ground state in 2 dimensions is still an area law state. But still, we see the same phenomenology, okay? And so that's all what I want to say. And it is just to stress the importance of identifying robust features in a many-body system. And in this case, the robust feature I've exploited at equilibrium was this scaling regime. Such that, yes?
A bit of a question. So the previous slide, you had an exponent beta there. I may have missed it. What determines beta?
So beta depends on the model. It's just basically the way in which
oh, yeah. So in this particular model here, this 2D critical system, is beta theoretically determined or empirically determined?
No, it's determined by Monte Carlo. So in this, the first determination was here in quantum Monte Carlo, and we also determine here in this plot. Now I don't have the numbers, but by doing this analysis, you can extract this beta also from our simulation. So it's numerical,
not theoretically determined.
No, it's just numerical. Okay.
I have another question.
Yes.
You said the HEP simulations has the same scaling law as the MPS scaling and so on, but like you can describe critical system using HEP.
Yes.
Right.
So
then what do you?
Yes, indeed. But what? There is a big and ongoing discussion on this thing. So we know that HEPs can be critical. But our belief is that they cannot be Lorentz invariant critical, in the sense they can encode two-dimensional criticality, but not fully three-dimensional criticality. So here we are in 2 + 1 dimensions, 2 space and 1 dimension. And this specific point is a point at which the low energy dispersion relation is linear. So there is a certain invariance under rotation between space and time. And we believe that IPEPs are not good at describing that specific criticality. But again, there are no proofs for that. And we only have, for the moment, numerical evidences. Because we know that, exactly as you say, kind of RK critical points or partition function of classical two-dimensional models can be described with IPEPs with finite bond dimension. Okay, but there the role of space and time is very different.
Okay, thanks.
Okay.
One more question.
Yes.
Previously, you mentioned if the system size is n, then En minus E infinity, the difference between the ground state energies scales up as 1/n².
Yes.
Is it just because the scaling dimension of the stress energy tensor is 2?
Yes. Yes, that's exactly, yes.
And this doesn't depend on the space-time dimension.
Yes, would be 1/n cube, no? In 2D.
So then this can be a way to verify whether IPEPs is good at simulating Lorentz invariant systems, simulating 2 + 1D CFTs.
Yeah, yes, that's a bit what we're trying to do, actually, to see if that's the case, or if it's just the fact that there are numerical difficulties in really simulating Appel system, because this could be another issue, right? So in principle, all methods that we have are iterative methods, and they're based, all numerical methods, they are based on improving the energy starting from certain state. And typically, if you want, physically what you are doing, you are filtering some states from your initial state and projecting onto the low energy state that you have in a certain physical intuitive way. And it could be that in order to do that procedure, since we do it approximately, we anyway need to open a gap. And so that could be also the origin. So we still don't know, right? But the conjecture is that this CFT critical point or Lorentz invariant critical point in 3D cannot be described with the PEPs with finite bond dimension, but it's a conjecture again. So
okay, thanks.
Yeah, no worries. Okay, so I hoped I convinced you that in all I said, entanglement played a little role, right? So as we said, there are cases in which we can base our reasoning on entanglement, and in this 2D case, we can't. But the important thing is to identify some robust phenomena. And now I go to, so this was all for equilibrium, and now I switch gear and I go out of equilibrium, okay? And now out of equilibrium, the situation is even worse. Let me first describe what I mean by out of equilibrium. Here I have the same Hamiltonian I had before, just I changed h by cotangent of an angle, such that I can describe all the phase in a compact, rather than going from 0 to infinity with h, I go from 0 to pi half with theta. I also had some boundary condition term here, but it's very irrelevant for the discussion. So it will be relevant, but please, for the moment, just forget about it and just let's focus on our Ising Hamiltonian. And that's the phase diagram that maybe I should have put before. So we have, as I said, Z polarized phase that is typically called paramagnetic. And then we have an X polarized phase that is ferromagnetic. Okay, and this pi divided by 4 that correspond to h equal to 1 before, we have this critical point that is described by conformal field theory. And so now, in order to put the system out of equilibrium, what I will do is a typical Quench protocol. So I will start with the ground state of h at a certain value of my parameter theta 0, and abruptly change the parameter of the Hamiltonian to theta 1, such that the new state is not an eigenstate anymore of the Hamiltonian. The original ground state is not an eigenstate of the Hamiltonian anymore, and so it will start to evolve. Okay, so what happens it's not difficult to have an intuitive picture of what's going on. And the idea is the following. We have an Hamiltonian that is translational invariant. So for the moment, we can think of it as defined on the ring. And so momentum is a good quantum number. The Hamiltonian will be block diagonally momentum. And we can think that we can somehow approximate the low energy excitation by single mode, in a single mode approximation. And they will be some momentum state. And so we will be able to plot the energy as function of the momentum when we get the standard dispersion relation. And we know that the derivative of the dispersion relation gives us a group velocity. So if we populate a few excitation around the given momentum as a wave packet, this wave packet will spread at this velocity, will move at this velocity here. Okay, so what happens is that now we take our initial state. Our initial state is not the ground state, but is a high energy state with respect to the new Hamiltonian. So locally, we can think of creating this, so populating this excitation. But since the state is translation invariant, this population happens at zero net momentum, and so k and minus k particles are populated together. And so Cardin Calabrese gave this picture in which particles that are originally created inside the correlation length of your starting state are initially correlated, and they then just spread freely, one in one direction and one in the other. So one left mover and one right mover separate, okay? And now we can discuss on what's going on from the point of view of entanglement. So if we have our block now here on the right, you see I'm plotting my block. So initially we can think of it as even a product state, but a very lowly entangled state because it was the ground state of the Hamiltonian at the gap point, for example. But then I quench the system, so these pseudo particles are created, but as far as they are close by, we don't see any entanglement, but then they start moving one to the left and one to the right. And so in our boundary, at our boundary of the blocks, here, particle coming from the left start to enter, and here, particle coming from the right start also to enter. And this particle is entangled with someone else that is outside, and this also is entangled with someone else. Actually, this is red, this should be blue, okay, the one on the right. But so this is moving on the other direction, this is moving in the other direction. But as time goes by, more and more pairs of entangled particles that originally were close by enter my system, meaning that the entanglement grows linearly in this region with time. And until when, basically, I have all possible, my state populated by a finite density of pseudo particle. Each of them is, if you want correlated, sorry, these are correlated on the other direction. So these are correlated in this direction, and these are correlated in that direction. But basically, I have, if you want, as many singlets aside of my system, and so the system has become completely entangled in a certain way. So this was the picture given by John Curry and Pasquale Calabrese in 2005 that explained the fact that during the evolution, the entanglement grows linearly and then it saturates at a value that is proportional to the volume of the region, okay? So this is a volume law state. So yes?
So in this picture, why doesn't this subregion generate some entangled pair by itself?
Sorry, I didn't understand.
So here you are drawing, this picture represents a subregion of the entire system.
Yes.
And after quench, there are some entangled pairs coming from outside. I'm
Yes.
asking, why can't entangled pairs be created from inside?
No, indeed. They can be created here, for example, and then one goes in and the other goes out. But then, so it's a bit more complicated, but then if you want, this guy here, for example, if they are created in the middle, they will leave the system at the same time. So they will not contribute to entanglement. Now, if you create them slightly off for some time, one will be in and the other will be out, but in the asymptotic limit, the two of them will have left. And so the only relevant thing are those that come from outside.
I see, thanks.
Okay, because if they are both inside or both outside, they don't contribute to the entanglement. Okay, one should be inside and the other outside. Okay. So from the point of view of a tensor network, again, this Quench process is just, again, a two-dimensional tensor network, like a PETS if you want, that we need to contract. So it's not very different from actually a ground state calculation from the point of view of the geometry of the network. But the difference is that in a ground state calculation, these pale blue tensor would encode somehow the Euclidean evolution of my Hamiltonian that project me onto the ground state at a long Euclidean time. Whether in a Quench, these just encode the unitary evolution of the Hamiltonian. And as we saw from the point of view of entanglement, this makes a big difference, because if we are doing an Euclidean evolution with a gapped Hamiltonian, we know that the ground state, so the asymptotic state would be an MPS. Whether here we are seeing that the states will become highly entangled as time goes by, right? And here I have these things. So in real time, this tensor network produce a volume low boundary state for a long time. In Euclidean time, this is at most logarithmic in the sense that if the Hamiltonian is gapless, we will have a very long time the critical ground states. Okay, so one could think, okay, but I don't really care about real-time evolution. I just do Euclidean time evolution and do an analytic continuation, right? So the Euclidean time evolution is more or less under control, because we're doing, because as we saw, ground state physics is more or less under control in the usual Hamiltonians. And then I could analytically continue my results at complex time, right? And in principle, this could be a good approach to out of equilibrium dynamics. But at least in certain cases, we know that this approach would fail, because actually it's not possible to analytically continue from real to imaginary time due to what I'm going to discuss now. That is something that was observed, as far as I know, in this, so was discussed in this context, in this paper here in 2013. And basically here I'm just again, so this is again all for a transverse Ising model that is exactly solvable. So these are calculation of what is called the Loschmidt echo, so the probability of return given an initial state. I evolve it in with this Hamiltonian H. That is so this initial state and this Hamiltonian. The first state is the ground state of H at a certain value of theta, and the Hamiltonian is the value of that Hamiltonian at a different theta. So it's a kind of Quench. But now you see the time is a complex number. So it can be either real. So if it is real, then we are basically moving in on the real axis here, and we are doing Euclidean time evolution. So we are calculating a kind of partition function of a certain model. Whether if Z is purely imaginary, we are doing a Quench, exactly the same Quench. And then we are projecting back, so I should have first indicated this is a starting state, that's the evolution, and then we project back onto the same state. Okay, so it's a return probability to the initial state. And the plot, what it shows is that, so this you can think of it as a partition function for complex beta, if you want, a boundary partition function. And what Hale, Polkonikov, and Kerin showed was that actually there are different phases in this complex value partition function. And the phases are described, let's say, isolated by lines of Fisher zeros. These are the zeros of, so these lines are the zeros of these partition function, or actually of the free energy. And you see that in this case on the left, there doesn't seem to be any problem to analytically continue from here to here, because this is a kind of a ground state calculation. This is dynamics. And here what happens is that it turns out that phi I and H are in the same phase. Okay. So I take a ground state of the system in a phase. I evolve with the Hamiltonian with other parameters, but still in the same phase. And I don't find any non-analyticity if I try to analytically continue from real time to imaginary time, or well, let's say from the real axis to the imaginary axis. Real axis, remember, is equilibrium. Imaginary axis is out of equilibrium. Now, if the initial state and the Hamiltonian are on a different phase, well, these phases, these different phases that are isolated by lines of zeros, then occurs actually in between equilibrium physics and out of equilibrium. So I cannot analytically continue from Euclidean time to real time, because I have to cross these lines of zeros. Okay, and so there actually I cannot do analytic continuation. So it actually seems that quenching across a phase transition is one of the hardest problems, at least from the point of view of tensor network calculation. Okay, and as I said, for tensor network, these quenches are particularly hard because we have this entanglement barrier. So the entanglement grows linearly with time. So at some point, matrix pro state won't work anymore, we know. And so there are several ideas out there on how to cope with this growth of entanglement in tensor network. But one possible way of looking at the thing is, again, can we find something universal in those phenomena and forget about entanglement once more and try to devise a scaling procedure close to this universal region? Okay. So this is the scope. Other question until up to this point. Okay, if there are no questions, then I will skip this slide and I will just, yes?
Sorry. So the lines that you were drawing were the zeros of what exactly? Because
this logarithm of Z.
Ah, okay, so of the free energy. Okay, so not of Z itself. Okay, so Z is...
No, sorry, are the zero of Z, so that when you take the logarithm, it diverges, okay? So it is a typical Fisher zero, okay?
Okay, fine, thanks.
No way. Okay, so now I will discuss briefly our results. So that's the context in which I'm interested in looking at these things. And what I will show is that actually there must be certain universality. So I will compare different kind of quench. One is this quench in the same phase, okay? This purple-blue line. I start from a gapped Hamiltonian. I change Hamiltonian slightly. I stay in the same phase, in this paramagnetic phase, and look at what happened. The second one is something that actually can be computed in certain limit using CFTs. I won't go into the detail of that. So in certain limit, this quench from, let's say, a gapped phase to a critical point can be described by the CFT. And that was the inspiration actually of our work. And then there is a third case that is actually this case in which we quench across the phase transition, and I will discuss also this third case. Okay. So first of all, I will again discuss everything in terms of the entanglement spectrum, because for the moment that's the quantity in which we have been able to observe universality. Okay, so we have this reduced density matrix of a region. And now we just check what's going on at the log to the logarithm of this reduced density matrix. Okay, and typically the reduced density matrix I'm interested in is a quarter of the system size, but it's not really important, right? I take 1/4 of the system and check what's going on at this reduced density matrix. So here you see typical quenches in the same phase, and the interesting thing here you see the inverse gap of the so GR, remember GR were just lambda R minus lambda 1, where lambda R and lambda 1 are the eigenvalue of the logarithm of the reduced density matrix. And so this is the inverse gap of the reduced density matrix, normalized by the size of the partition, but that's not really important. What you see is that they start to grow, so the gaps start to shrink, so these Hamiltonians start to become more and more gapless, but they saturate to to a finite value at some point. Okay, so they saturate here, and these lines are exactly the line in which. So here, for a guide as a guide to an eye, I have put the entanglement entropy in gray, so you can read it on this axis here. You see that here it's growing linearly, and then it saturates. So what happens is that these gaps start to close, but then they saturate, and the entanglement Hamiltonian stays gapped. Okay, I will not have much to say on these scenarios. Okay.
Sorry, what are the different curves?
So different curves are different gaps. Okay. So different colors are. So this is, for example, the first gap, the second gap, and so on, so on, so on. So just different eigenvalues in the same partition.
So
Well,
here,
the gray one is the entanglement. So that's the only difference. So this one here is the entanglement entropy, just to give you an idea on where the simulation is in time. So this is the build-up of entanglement, then the equilibration, and then these are recurrence because the system has a finite size, and so things keep going on periodically in the things that is the size of the system on a time scale that has to do with the size of the system.
is the density matrix normalized to 1?
Yes.
Okay, thanks.
Okay. Okay, so as I said, I won't have much to say for these quenches because you see the Hamiltonian is gapped, and I don't have much to say on that. Okay. Now, what I'm plotting is what happens at the critical point. So at the critical point, now I'm plotting minus the log of these eigenvalues. You see that we start having just one eigenvalue, and then many of them come down and start to contribute. They shrink, and then they do something here pretty funny. Again, this is the linear growth of entanglement, saturation, and then recurrence. Okay, and so let's try to have a better look to that. But first, one important piece of information is that Andreas Lochley had studied the entanglement spectrum at equilibrium, and there are some analytical results from CFT, and show that actually the entanglement spectrum at equilibrium was in correspondence with the spectrum of a conformal field theory with these boundary conditions. So it's a bit technical. So in conformal field theory, you have these critical exponents, but depending on the geometry in which you study your CFT, certain critical exponents are filtered out by boundary condition, and so you're left with certain spectra. So at equilibrium, it was already known that the reduced density matrix of a region encodes, so the eigenvalues encode these critical exponent. Okay. Now what we are looking at is what happens out of equilibrium, and here again that's the same kind of plot that we saw, but the difference is that, as you see here, there is a clear linear growth of this inverse gap, and then there is some plateau here that we will analyze better in the following. Okay, there is a clear structure of these gaps that remind some kind of regularity. Okay, and so the way, as I said, the way to understand what's going on here, you see that gaps are changing with time. So the normalization of the Hamiltonian, if you want, is changing with time. So the gaps are closing down as times pass by. So the way to look at it is to study the ratio. Okay, and that's I think something amazing. So if you look at these ratios, beside something that I will discuss here, there is a hole here. You see that they are somehow equispaced on integer numbers, and they are pretty stable along all the evolution. Again, this is the linear part of the growth and entanglement. This is the saturation, and this is doing like that. So these are the time scale in which pseudo-particle enter and exit. Here you see we are looking at the region on a system with PBC, and what we see is actually that if you do a bit the math and look at what you would predict for the ratio of critical exponent of an Ising model, you seem to see that in this region here you have two copies of two primary families. So you have two operators, the identity and the energy density, and you need to take the tensor product of two of these operators in order to describe these gaps here, whether here you only have one copy of them. And somehow the by hand intuition is that the pseudo particle that enters on the left and on the right, each of them represents somehow one CFT with free boundary condition, and when they meet in some strange way here, they just glue together and become a single CFT from the tensor product of two. But we don't have analytical control on that, so it's just a kind of conjecture based on our numerical results. But what happens, you see, is that the reduced density matrix become very universal. So the gaps are described by the critical exponent of the Ising model. And here, well, I skipped this slide. Here it's even more impressive, because this is now the case of a chain with open boundary condition. So my interval only has one boundary. So this tensor product of two copies of the CFT doesn't happen, because I have only one boundary. So I have only right moving particles that enter, or left moving particles, sorry, that enters my block. And as you see, if you study, again, the gaps here, the first plot time is always in this direction, and the y-axis in this first panel is just the inverse gap. So the gaps are closing because the inverse gap are growing, then they saturate and then they decrease again. The entropy is here again as a guide to an eye. But if you normalize this gap to the first gap, so they're all doing the same thing and they actually stay constant, so nothing happens. Okay, so it's pretty amazing that all these very complicated out of equilibrium dynamics results in a single state in which the normalization factor in front of the entanglement Hamiltonian is changing with time in a very simple way, linearly, and then constant, and then linearly down. But nothing else seems to happen. Okay. Okay, so that's the summary for the quenches at the critical point. So I hope I convince you that there is something that we don't fully understand. So there is this super universal thing. It doesn't depend on where you quench from, as far as you quench to the critical point. But now I think more amazing is what
a question. Thanks.
Yes.
Maybe just to check. So the quench regime is just a direct switch to another value. You don't have a time scale. It's not a linear.
No,
just,
yes.
You jump.
Yes, I jump.
Okay, great.
Okay.
And Luca, just a reminder that maybe
2 minutes, no?
10
Yes.
minutes, but yeah, we have some flexibility. So please go on.
Okay. But so now I want only to discuss another case, that is the quench across this critical point that I discussed before, and where there was this observation of this line of Fisher zero that somehow was identified as the presence of dynamical quantum phase transition, or called, because at specific instances of time, if you remember, there were these lines of zero crossing. So there are these several T star at which we would cross a phase transition from one phase to the other. Okay, and so what we had already observed long ago with Gabriele Di Chiara and his at the time master student Giacomo Torlai was that if we looked at the entanglement spectrum for quenches across the phase transition, we would see this touching point. Sorry, these touching points here. I cannot. I don't know why. If I here you see these touching points. Sorry, and these touching points actually, if you study them. So if you study the inverse gap here, you see that there are these spikes, and these spikes actually are exactly mimicking or happen exactly at the same times in which you have this dynamical quantum phase transition. So you see something going on in the entanglement spectrum at that point. But what we had already observed, that this only worked in one of the two directions of the quench, right? If we changed, so if we now quench from ferromagnet to paramagnet, now we are quenching from paramagnet to ferromagnet. If we quench in the other direction, nothing seems to happen. But we had already observed that, and you can appreciate here, that somehow, again, the entanglement spectrum is getting gapless, right? You see this shrinking of levels towards something that looks like gapless, despite this strange oscillation, okay? And so here it's what we obtain again by repeating the things, but now looking at the ratio of the eigenvalues rather than just the spectrum, as we did in our old paper. And what you see is that, so if you quench from one direction, so again, from paramagnet to ferromagnet, or the other way around, things on the left are very messy because of these diverging inverse gap right? So there are these touching at certain times that again are the times of the quantum, of the dynamical quantum phase transition. But beside that, they don't look that different, right? First of all, you can still imagine that there are some kind of linear increase here beside this oscillation, and this linear increase become very clean on the other side, so quenching in the other direction. And then again, we see the system plateauing at these integral values again. And same here, despite the fact that we still don't understand well what's going on here. But if we believe that here the things are somehow plateauing again to the same integral value, it seems that we are again observing the same kind of universality we have observed for quench at the critical point, for quenches across the critical point. And it's pretty interesting because as far as I know, there are very little ideas on how to extend universality and scaling at this dynamical quantum phase transition. So here we have found something that seems to become gapless in a universal way. Okay, so we have somehow the main ingredient to construct now a scaling theory close to this dynamical phase transition. And so the message is that it doesn't really matter. So the location of this dynamical quantum phase transition are not really relevant to what I'm saying now, because here what we are seeing is what happens after having crossed many of these dynamical phase transition in the equilibrating regime. So at t going to infinity, let's say. Obviously, I cannot take t infinity here because the system is finite. So I can only take t of the order of L times, so the velocity times L divided by 2 or something like that. But the idea is that if I were able to take the terminal limit and go to longer and longer time, the things, first of all, this oscillation will dump, these things will converge down, and we will see something very similar to what we have seen for quenches at the critical point.
I have a question.
Yes.
So for the dynamical quantum phase transition, is it a necessary condition to take the quench across a critical point?
No, I don't think so. Actually,
but that is but when you saw the correspondence between the gaplessness of your entanglement spectrum, and you said that they correspond to the dynamical quantum phase transition.
Yes.
But
so exactly. So that's how they were somehow introduced. Now I would suggest that every time you see a reduced density matrix or after a quench becoming gapless, then you can define, so you can imagine that you have crossed a dynamical quantum phase transition. And I think there can be example in which, despite you having an equilibrium phase transition, you don't see this, okay, in quenches. And I guess you can find example in which, despite not having an equilibrium phase transition, you can still see this entanglement spectrum becoming gapless. So that would be my take on it, okay? After these things. And so this is more or less what I wanted to say. So again, this should be considered as a work in progress in which we are trying to understand if we can identify universal feature in the out of equilibrium dynamic, then we can now exploit to set up a kind of scaling theory of our dynamics based on approximate method. In the same way you do a finite size scaling close to the critical point with Monte Carlo, or finite bond dimension or correlation length scaling with tensor network. Now, I think we have identified something that is a good candidate as a starting point to generalize this idea out of equilibrium, where unfortunately, for the moment, we don't have any simple tensor network that can be used to actually simulate long-time dynamics. I didn't motivate what we are interested in long-time dynamic. I have assumed that everyone is interested in long-time dynamic. I can discuss about it if someone is interested in why I am particularly interested in that kind of problem. But I think I would stop here. And thank you for listening.
Okay, thanks, Luca. That was a very nice talk and very clear. Maybe I can start with a question. So all these results are for the criticalizing model, yeah?
Yes.
But you expect most of the story to be more general or sufficiently general?
Yes. So as I said, we at least in the quench at the critical point, we were inspired by results in CFTs. So we expect that this should hold for all CFTs, at least the part of the quench at the critical point. We believe, again, that there is something specific to these conformal field theories, in the sense that they're basically you are very restricted by conformal invariance, and so many of the things that happen at equilibrium can also happen out of equilibrium because of conformal mappings. So you can map one situation into the other. So you can basically map this quench scenario into a boundary partition function. Yeah, I don't know how much of this would, for example, survive in a different transition, like a BKT transition or stuff like that. So this is still completely unknown. But I'm pretty convinced. So actually, we are working on that now, doing simulation with other critical models and see if you can see the same.
Okay, thanks. Any other questions?
I have a question, Suki.
Yep.
Yeah. So thanks for the nice talk. So like in this talk, you like talk about taking quenches across equilibrium phase transitions and so on, right?
Yes.
Can you comment on like dynamical transitions?
Yeah. So which one? So
like an MBL transition, not like a ground state phase transition, you know?
Okay, no, I can't actually, because I'm not sure. So for the moment there, I'm not sure if the same holds true. So if there is a kind of a universality in this entanglement spectrum, you can certainly, so I skipped the slide. So there are certainly other definition of universality out of equilibrium, and in particular, you could just try to rescale out of time correlation function in space and time, and try to find some kind of collapse of the data, right? And this would give you a set of exponents for spatial and time correlation that you can use. So when things collapse to a single curve after this rescaling, then you can use the same, let's say, scaling theory that you use for equilibrium phase transition. But we haven't worked on that yet. So that's something, yes, we plan to do. But
yeah. Okay, thanks.
You're welcome.
And another question, maybe I missed that in case that was apparent from your conclusions, but like the frequencies of the entanglement spectrum, or the spectrum of the entanglement Hamiltonian, is it related to the frequencies or energies of the original system Hamiltonian?
So in a specific case, not in a sense. They are the same. So my original Hamiltonian, if you want, was is the Hamiltonian at a given value of the parameter in which typically the initial state is massive. So the initial state is off critical, right? So what this entanglement Hamiltonian relates to is the Hamiltonian at the critical point. So if you want the CFT Hamiltonian, not the one that you use on the lattice for your initial state, but rather, if you want, it looks like, so the conclusion of this work is that that at least a low entanglement energies, so if you look only to the first few levels in your entanglement Hamiltonian, your evolved state become a thermal state of the critical Hamiltonian. So that's what it looks like. Both in the case in which you quench at the critical point, that is not very surprising, besides the fact that in this case at least, the system is integrable, so you would expect a GG. And when you quench across the critical point, and that is possibly a bit more surprising, because in that case, the final Hamiltonian is different from the critical one, but it seems that at least in the long time regime, the system is going to equilibrate to a thermal state. In the low entanglement part of the entanglement Hamiltonian, it's going to equilibrate to a thermal state.
So are you saying that you only consider the entanglement Hamiltonian at criticality, at the critical point?
Well, I'm not considering it. It comes out, right? So what comes out is that my entanglement Hamiltonian is becoming gapless, and is becoming gapless in a way that is characterized by so the masses of these entanglement Hamiltonian are going to zero, but the ratio is the one that you have for the critical point when the entanglement Hamiltonian becomes gapless.
Okay, thanks.
I also have a question. Hi, Luca.
Hola, Mari Carmen.
Thanks for the talk, very nice. So I actually had a question that I think you partly answered right now, but then I have another one. So my question was, why would you expect that quenching in both directions, you would have the same if the dynamics after the quench is governed by the Hamiltonian at the end, right? And you are really using some different Hamiltonian. So I think you already gave this answer that what matters or what appears there is this critical point, but then you would expect that no matter where you start and where you end, right, in this quench, you also see basically the same thing. Is this happening in your numerics?
At least in our finite size numerics, it happens. So I don't know if it is kind of pre-thermalization. So if you would be able to go to infinitely large time, I would expect that the final results should depend on your final Hamiltonian, as we know, because again, it's a generalized Gibbs ensemble that depends both on the initial state and on the final Hamiltonian. But what we are observing on our finite systems, at least again at low entanglement. So I haven't talked about higher eigenvalues, so this could also be different, and one has to be careful with that. But at low entanglement, it seems that at least you observe a kind of pre-thermal regime that is completely dictated by the critical point. And that's surprising, actually. So we wouldn't have expected that.
Okay, thank you.
You're welcome.
Any more questions?
I have a question. On the first model, you had this criticality at h equals 1. If you imagine the system at the critical point, if you like, in the critical state, and then you quench into one of the spin states, either the spin up or the spin down, but quench into one of those states, choose each state less than 1. What do you know about the dynamic scaling of the system? Does it converge in a power law fashion towards a spin up state or a spin down state?
So this is one of the results by John Cardy and Pasquale Calabrese, that actually you never get power law behavior of the correlation. They typically always decay exponentially in these these quenches. So this is somehow the strange thing.
Wow. So, no, I mean, my background is a classical phase ordering systems, so spin systems which are not quantum, and so the phenomenology there is into the first order phase transition. You generally expect a power law for the domain. You have domains basically which form. I was thinking more of a system which has a mixture of spin up and spin down with domain walls. But what you've described is quite different.
Yes, actually it is. And yeah, I mean, that what you are mentioning, the possibility of scaling of correlation function in time. So again, that's a different universality. And it's called actually dynamical critical. So it's also called dynamical critical point, but is I would say dynamical critical point of type 1. So that by changing the initial condition and the final one, at some point you go from exponential decaying correlation to some power law decaying, and that's also something that can happen, as I said before. But this is different actually. In this quench, everything become exponentially decaying.
Uh-huh.
And the reason for that is just that from the point of view of so there is this conformal invariance, so you can always at least in the simplest case, you can map your infinite system to a finite one, so to a finite geometry, and the size of that geometry gives you this exponential correlation length, if you want. So roughly speaking, so it's always possible to do a conformal mapping from this infinite system out of equilibrium to a finite one that looks like at equilibrium, and then you get this exponential scaling.
So there's no analog of domain wall or domain dynamics, phase ordering dynamics that appear in this sort of quantum setting.
At least not in this system. There can be in more complicated systems, but not in this specific one.
I'd be interested to know examples of that.
Yes, I think actually there was an experiment last year. Maybe I even have, let me see if I have the slide, because I skipped one slide that may be the one. Let me firstly go to, yes, so one example of that is this experiment here.
You going to screen share that one?
Let me share again. Share. So this paper here, in which you see that, I'm not sure if you can slideshow stuff on current slide. So here you see there is momentum and the structure factor, and then if you rescale things properly by appropriate ratio of time and space and blah, 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 everything collapsed to a single curve. And the experiment was this one here. Wow. In the group of Oberthaler, I guess, Markus Oberthaler. So in Heidelberg.
That's a log plot, so they got the exponent. Yeah.
Yes. I think so, yes.
And that comes back to that question asked before. What theoretically is understood about these exponents? Are they purely empirically determined, or are there any symmetry principle?
Yes, I'm not an expert, but there is a theory of these dynamical things that basically extend the statics one with the extra exponents coming from the dynamics. So you could have an extra what is called dynamical critical exponent that can be different within the same let's say spatial universality class. So there is a kind of lifting from a universality class at equilibrium to a universality class out of equilibrium, but it's not a one-to-one lifting. So the same universality class can go to different one. But I'm not really expert on that. So I know the pointer to the literature when I have to go and study it.
Thanks so much. That was great. Thank you so much.
You're welcome.
So here, if I may add something. Hi, this is Jad Halimi.
Hi, Jan.
Yeah, so recently in a couple of works that I did with Victor Gorari and Markus Heil in easing models with random fields, we were able to see that these non-analyticities in the dynamical analog of the thermal free energy, we actually do get some really interesting exponents that are what we call non-trivial. So basically, they're not integer valued, nor are they of the mean field type. So one paper came out just exactly a week ago. So
okay, yeah, I missed that.
Okay,
I will have a look. Yes.
All right, thanks.
Thanks for that, Yad.
My pleasure. I will just share it on the comment chat, the papers. So shameless advertising, but just in case you guys wanna.
Yeah, no, sure.
Given that, I'll shamelessly advertise my classical versions.
No worries.
Luca, maybe can I ask one more question?
Sure.
What is the what corresponds to the conformal boundary conditions? How do we think about the conformal boundary conditions in terms of the spin chain or the I mean, how do we determine what are the?
Yeah, that's a good question, because actually we are not sure. So that is something. Let me see if I have a slide about it. But it is something that doesn't come out from the CFT analysis, because it's actually something that has to do with lattice effects. And so basically, let me see if I can unhide. I had hidden all the CFT slides. One sec. How do I do it? Maybe you can see it like this. Let me share again. Can you see it? here.
Yeah.
So here, basically, that's the geometry to which your Quench maps to. So you have a strip, okay? And so this strip has a boundary condition here on the top and on the bottom, and these are the conformal boundary condition that you have to choose. But then you have also boundaries here and here, right? And actually, the only things you can do in order to get rid of some of these boundaries to take this A infinite, and so you only have one boundary here. And then the question is, what is the role of this conformal boundary condition and this role of the boundary condition at this point here? And so that's particularly complicated in CFT, and in our case, somehow. So the first insight came from this paper by Andreas, where he identified that at equilibrium, so you can think of equilibrium like just, let's go back here, the full plane with just a cut, okay? So we just have these two extreme points here. And so in that case, then he showed that the relevant boundary condition for some reason are the free boundary condition, unless you put some operator at the cut, where at the extrema of your chain. But I don't think there is any analytical understanding for that, okay? Because in the CFT, again, you have to regularize the theory, make a small circle around your cuts, and then that's where you have to put the boundary condition. But at least numerically, it was observed already that at equilibrium, the relevant boundary conditions are always free. And then the good question is what happens out of equilibrium. And what we saw is that, well, as I mentioned, with the PBC, it seems that we need to take 2 copies of this free boundary condition, but then with OBC, we still just need to have 1 copy of free boundary condition. But what we're currently working on is to study more complicated boundary conditions, so fixed boundary condition and things like that, and see how the things change. So what's the role of this boundary operator? But again, I don't think there is any analytical intuition about that. It's all coming from numerics.
Okay, yeah, thanks.
You're welcome.
Okay, are there any more questions? Okay, if not, so Luca, I would like to thank you again on everyone's behalf. Sure. Thanks again for this nice talk.